Good evening, one and all. Is the audio clear? And my video also to all. If you have any lag, then please tell to anyone. Is it clear for you? Say. All right. So, in the previous class, we discussed the concept of maximal ideal, prime ideal, and the quotient ring. So, in today's session, we will discuss the results based on the prime ideal as well as maximal ideal and other concepts based on these ideals, right? So the first thing is, I just want to recall the definition again. The concept of prime ideal is given by whenever you take the commutative ring R with unity and U is an ideal of R and U is not equal to R. U is an ideal which is less than R. It is a proper subset of R. So whenever you take two elements in the ring and if the product belongs to the ideal, then either X belongs to U or Y belongs to U. This condition must be satisfied by the ideal U. Then we say that it is the prime ideal. Okay. This is actually we have given the definition earlier. Now the interesting thing is, as we discussed about the quotient ring, so whenever you take the quotient ring, it has very similarities just like the ring R. Since R is a ring, R by U is a ring, R is commutative, R by U commutative, R has unity element, R by U also has unity element and so on. The special thing what we need to consider here is R by U will become an integral domain if and only if U is a prime ideal. So this is one good relation between the ideal and the ring we can observe. So this result we just want to prove now. So please take a note of this. So the quotient ring R by U is an integral domain if and only if the ideal what we have taken must be a prime ideal. After noting, please tell. Right? So it contains two parts in the statement. So let us go with the main part. In this, what we have to assume? We have to assume that R by U is integral domain. So our claim is U is a prime ideal. So if we go with the definition, so you take two elements, let X and Y belongs to the ring such that the product belongs to the ideal U. So immediately you can say that XY plus U is equal to u. Do you accept for it? Here I give a small thing that earlier you have done a small result in cosets with regard to subgroups that can you recollect this result? Say yes or no. So if the operation is multiplication, this is the condition we are going to accept there. If the operation is addition, then the condition is like this. You can observe the similarity between these two. Clear now? Why you have taken this thing? Right. So on the left side, applying the property of coset multiplication, it is nothing but x plus u dot y plus u. On the right side, it is nothing but 0 plus u, because u is nothing but 0 plus u, the 0 element in the quotient ring. Now what happens? You can observe that this is an element in R by U, and the result is 0. So you just feel that the result, the product of two values is giving 0 in the quotient ring R by U. As we supposed that R by U is an integral domain, it has no 0 divisors. So from this, whenever the product becomes 0, either of the value must be 0, because it has no 0 divisors. So you can say that x plus u is equal to 0 plus u, or y plus u is equal to 0 plus u. So from this, you can say either x belongs to u or y belongs to u, because 0 plus u is nothing but u, again applying the same condition of group theory. So you can say like this. So you have started that the product belongs to u, and here you concluded that one of the elements is belonging to u, therefore u is a prime ideal. That is the solution of the main part. Please check. If you have any questions, you can ask. After noting, please tell. Any queries, any doubts for anybody? Please tell. Yes, that is what I am saying. Accepted this result of group theory, say. So here the operation is dot. So if you take the operation as plus, this will come, because it is a result generalized for every operation. We can say that if you take the operation as star, then x belongs to h, if and only if x star h is equal to h star x. So you are saying that if the element is present in the subgroup, coset subgroup both are equal. So here also, if the element is present in the ideal, coset ideal both are equal. That is the concept here. Clear? Say. So this is the applicability here, what we are doing. Any other questions, please? Shall I continue for converse part? Okay. If you know the main part clearly, converse part also holds similar steps, very similar steps in the converse part we use. So in the converse part, we assume that U is a prime ideal and our claim is R by U is integral domain. So in general, you need to calculate all the 11 properties of the integral domain like abelian group, semi-group, distributive properties, commutative, unity, no zero divisors, etc. etc. So as we know, R and R by U has similar features. We just check only one condition, that is R by U having no zero divisors or not. Rest of the things trivially follow. There is no need to verify that R by U is a ring. R by U has distributive laws. R by U is commutative. These things there is no need to verify separately. We simply verify that R by U has no zero divisors or not. Then it will become the integral domain. Okay? Clear for everyone? So we just verify for no zero divisors case. So what does it mean? Whenever the product is 0, one of the elements must be 0. That we have to show. So let us take two values, say a plus u, b plus u belongs to R by u, such that the product is 0. Now, starting with this step, we have to show that either the first value is equal to 0 or the second value is equal to 0. So from this, what we can conclude, whenever the product of two values is 0, one of them is becoming 0. Therefore, it has no zero divisors as per the definition. Okay? Right. So applying coset multiplication there, it is AB plus U equal to 0 plus U. That is AB plus U equal to U. Just earlier we applied the group's result. Applying the same result there, from this you can say AB belongs to U. As per our supposition, U is a prime ideal, hence we can say that either A belongs to U or B belongs to U. Applying the same condition again, you can say A plus U is equal to U or B plus U is equal to U. Therefore, it has no zero divisors, hence it is an integral domain. That was the conclusion. Please ask if you have any queries. If anybody has any queries, you can ask. Are you clear, everyone? Say. Shall I continue for the next? Any doubts for anybody? All right. Now, are you clear with this problem, or do you have any queries? Please tell. Are you clear with this or not? Fine, thank you. So one interesting thing is, that's what I am saying. This result I have applied here. Please check. So this comes like the very similar result. There the operation is multiplication. Here the operation is addition. That is actually I am saying. So whenever you say that A belongs to U, implies immediately you can say that A plus U is equal to U. See here, A plus U is nothing but you are calculating a coset. If the element is present in the set, coset and the set both are equal. This is the example you have done already, isn't it? If you want a small example, say the very fundamental example in group theory, this is we have taken earlier. So take H is equal to 1 comma minus 1. So here the element minus 1 belongs to H. Now minus 1 dot H is nothing but minus 1 comma 1. This is nothing but H. Accepted? Just like whenever A belongs to U, this thing will happens and this thing will happens. The only difference is operation. In group theory, we calculate cosets with multiplication. In ring theory, we calculate cosets with operation plus. That is the difference. Clear to all? Fine. So here we introduce a small concept that sum of ideals. So what is meant by sum of the ideals? So you simply take two ideals, say U1 and U2. The sum generally indicated with the symbol plus, U1 plus U2. It is defined by set of all x plus y such that x belongs to U1 and y belongs to U2. In other words, you pick up one element in the first set and one element in the second set, you simply add them. The result you are specifying as sum of the ideals. So always U1 is a subset of U1 plus U2 and U2 is a subset of U1 plus U2, and by default it is a subset of the whole ring R. So from this very notation, we can observe that if I said that A belongs to U1 plus U2, it means that I need to understand that A can be written as sum of two values, where the first value belongs to the first ideal and second value belongs to the second ideal. We can understand that the element can be split into two ways, two types, I can say. So in the first one belong to the first set, second one belong to the second set. That is the concept of sum of the ideals. I think you can prove that U1 plus U2 is an ideal. Can you prove, or let us discuss now? Please specify. Are you able to prove that u1 plus u2 is again an ideal? Is it within your range to show by verifying the two conditions of the ideal? If you feel it is difficult, let us do it now. Please specify. So you want me to do it right now? The sum of the ideals is again an ideal? Right. Let us do it now then. Now see, whenever you take a set, say A, if you want to say that A is an ideal, you need to show that A satisfies two conditions. So what is the first condition? Whenever I take elements A and B in A, then A minus B also belong to A. That I have to show. That is the first condition of the ideal. Accepted? So here also we should follow the same thing. So let us say A belongs to u1 plus u2 and B belongs to u1 plus u2. So from this very nature of u1 plus u2, you can say A is nothing but sum of two values. B is nothing but sum of two values. It is possible to write as per the definition of the set is concerned. So therefore you can write A is equal to x1 plus y1, B is equal to x2 plus y2, where the first values belong to the first ideal, second values belong to the second ideal. So you can say that x1, x2 belong to the first ideal, y1, y2 belong to the second ideal. Now, applying the first condition, you consider A minus B. So this is nothing but x1 plus y1 minus of x2 plus y2. You can write it as x1 minus x2 plus y1 minus y2. So this value belongs to u1 plus u2. Since x1 minus x2 belongs to u1, y1 minus y2 belongs to u2 as their ideals. Please check on that. After noting, please tell. So if you know the definition clearly, then it is very easy for you to solve. So any questions for anybody? Right. Now, coming for the second condition of the ideal. So what is the second condition there? Whenever you take the ring R, you take one element in the set, one element in the ring, product must belong to A. So you have to show that RA, comma AR belongs to A. This thing we have to show, that is the second condition of the ideal. So here also we say that, so you take U is equal to U1 plus U2, A is equal to, where A is nothing but x1 plus y1, and you take any element in the ring. So if you consider the product AR, it is nothing but x1 plus y1 into R. This is equal to x1R plus y1R belongs to u1 plus u2. Since you can have a diagram like this. So since U1 and U2 are ideals, X1 belongs to the U1, R belongs to the ring, therefore the product X1R belongs to U1. Since Y1 belongs to U2, R belongs to the ring, the product Y1R belongs to U2. Therefore, AR belongs to U1 plus U2. Similarly, you can say that RA belongs to U1 plus U2. Therefore, the sum is again an ideal, which is the bigger one containing both the sets. Any questions you can ask? I simply applied the conditions of the ideal there. Fine. If you are clear, then I want to take the other one. After noting, please inform. So I just want to inform a small thing that due to the vacation of Pongal here, so our classes will be halted temporarily. So our classes will resume from Thursday onwards. So Monday, Tuesday and Wednesday are holidays, and from Thursday onwards we start as usual. So Friday also we have a class in the next week. Okay? Because of the local traditional, we are taking holidays. Right. So after having this, we have another interesting concept that it is also a previous year asked question. Now you take a ring R, you take a subring. So whenever thinking of group theory, so while you talk of group and subgroup, whatever the identity element in the group, the same identity element will be taken in the subgroup. Let me say, if E is the identity element in the group G, the same identity element will present in the subgroup H also. But here, coming to the case of ring and subring, the ring may have different identity element and subring may have different identity element, because here you are checking for two operations, not for one operation. There was a difference between these two. So the question is asked that give an example that the ring and subring have different identities, right? So please take a note of this, then we'll discuss on it. Give an example that ring and subring have different identity elements. In other words, different unity elements, let me say. Different unity elements. Clear to all? The question tag? Okay. Now, for majority of the examples, we go for the matrices always. In matrices, we will get so many examples. So you take the ring R as all 3 by 3 matrices over the real numbers. So you take the values as all 3 by 3 matrices over the real numbers. Now you take the subring as, so you are taking or you are extracting a set of 3 by 3 matrices from the whole ring R. Since matrices are of different types, in square matrices you are considering, You can take triangular matrices, rectangular matrices, square matrices, upper triangular, lower triangular, diagonal, as well as scalar matrices, everything you can take. So here I am taking the matrices of the form where all the values are equal. So what type of matrices I am considering here? I am considering of the form 5, 5, 5, 5, 5, 5, 5, 5, 5. So this type of pattern of matrices I am considering into one set, and I am saying that this is a subring. Clear? Yes or no? So if you have a doubt that will it be subring, then definitely it is subring, because apart from checking all the conditions that what are the necessary and sufficient conditions, we can check so that the set will become a subring. Can you tell? In the previous classes also I have discussed on it. So what are the necessary and sufficient condition? We can check on a subset so that it will become a subring. Can you specify? Or can you recollect the idea? Yes, A minus B belongs to S, one condition. Is there any other condition we can say? AB belongs to S. So, not AB inverse, that thing will belong to only group theory, because whenever you mention AB inverse, it is with respect to the operation multiplication only. So, you are correct. A dot B inverse is absolutely correct. So, here what you are doing, you are taking the first element as it is, second element inverse you are taking, in the middle you are applying the operation. There the operation is dot. So if you take the operation plus, so you take the first element as it is, inverse of second element, the operation plus you take. So here inverse of B is nothing but minus B. So you are verifying for A minus B. This is with regard to one condition plus. On rings you have two conditions, plus and dot. So for dot we verify A dot B, because dot must satisfy only closure and associative. For plus you need to verify 5 properties. So for plus we verify this, for dot we verify this. So the simple example is, please look at the set pattern what you have taken. So if you take any one real number, that corresponding matrix I am taking here is of this pattern. If I say 2 is a real number, the corresponding matrix is 2, 2, 2, 2, 2, 2, 2, 2, 2. This is the matrix belonging to subring S. If I say 1 by 2 is a real number, corresponding matrix is 1 by 2, 1 by 2, 1 by 2 I am taking. So for each real number, corresponding matrix of this pattern I am taking in the set S. So how to verify these two conditions of subring there? It is very simple that you take any two values, say you take A is equal to X, 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 and you take B is equal to Y, Y, Y. So if you consider A minus B, so all elements will be of the form X minus Y, X minus Y, X minus Y, and so on. So the result also satisfies the same pattern, isn't it? Do you accept or not? Therefore, A minus B will belong to the set S. Now, if you talk about the closure property A dot B, you simply multiply these two matrices. You perform the multiplication between them. You will get a matrix of the form where all values are equal. I simply say that if you consider, you will get the matrix as 3xy, 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 and so on. each entry is nothing but 3xy. Do you accept it or not? Please check with the multiplication. Every element is nothing but 3xy there. So all the entries in each position is same. 3xy, 3xy, 3xy you are going to get in the whole matrix. Therefore, the two conditions are get satisfied by S, so that we can say that it is a subring of the 3 by 3 matrices R. Okay? Yes or no? Right. Now our intention is we are going to check that ring and subring both are having different identity elements. So if you take the 3 by 3 matrices, the identity element is nothing but 1 0 0, 0 1 0, 0 0 1. This is the identity element there in the whole ring R. But if you take the subring, the identity element is different. So let us go with it. So let us say I have taken the element A. The entries are nothing but x, x, x. And I say that E is the identity element. So let us say this is another matrix. For example, you take Z. Now what happens? It is giving the same result. Because this is the identity element, you should get A dot E is equal to A. Because E is identity. Accepted. So if you multiply these two, you will get 3xz always. This is equal to the value x. So if you equate the corresponding values, you will get that z is equal to 1 by 3. So what is the corresponding identity matrix there? It is nothing but so you can check for this, as we have 3xz is equal to x. So x gets cancelled, z is equal to 1 by 3. You accepted or not? So this is the identity element in the subring what you have taken. So the very good example is the ring and subring may have different identities. Clear for everyone? So if you are clear with this question, I want to take the other concept. After noting, please inform. One good result which we can take is whenever two cosets are equal, immediately we can say that the difference between the elements will belong to the ideal. It is very good result. The proof is not required for you. So this is identity element in subring. In the ring, the identity element is this. This is the identity element in the ring. This is the identity element in the subring. Both are different. Okay? Fine. So coming to this part, whenever two cosets are equal, then the difference between them will belong to the ideal U. So this result we make use of proving the present one, which is very good result asked in the previous year papers. So R by U is a field if and only if U is maximal ideal. So this is very interesting result. So a little bit lengthy also, because it contains main part as well as converse part. It takes a lengthy procedure, but you enjoy doing the logic. So this is the question, you take a note of it, asked in the previous year papers. R by U is a field if and only if U is maximal ideal. Please take a note of that. So coming to the solution part, it contains main part as well as converse part. So please tell me which part you want to prove first, main or the converse. Tell me. Converse, right? So let us start with the converse part. In the converse part, we are assuming that U is maximal, and our claim is it is a field. So we have to show that R by U is a field. As we know, R by U has very similar properties like R. So it is a ring, it is commutative, it is unity. So to prove that it is a field, we just have to verify only one condition, that whatever the non-zero element you take in R by U, it has inverse in R by U. So field exclusively, the special properties, it is having inverse, the multiplicative inverse for all the non-zero elements. So if you take any non-zero element in R by U, we have to show that the inverse is existed within R by U only. That we have to show. So if you say that X plus U is a non-zero element in R by U, so our aim is to bring a condition that X plus U dot something should be equal to 1 plus U. Because this is identity, this is element you have taken, and you have to find that if this element is existed such that the product of these two is equal to 1 plus U, then this is nothing but the inverse of X plus U. So R by U possesses inverse for every non-zero element, hence it has the inverse property, so it becomes the field. That is the idea. Okay? If you are clear with the idea, then I start with the procedure. Please tell. Right. So immediately from this step, we can say that X does not belongs to U. Why? Because I have given the condition that X belongs to U if and only if X plus U is equal to U. This type of thing we already mentioned in the previous problem while doing a problem on prime ideal, isn't it? The coset properties we mentioned. So if this value belongs to U, these are equal. If this does not belong to U, then both are different. Since it is a non-zero element, immediately you can say that X does not belongs to U. So you can have a small idea there that You can have the visualization like this. If you take this is the ring R, this is U, X is outside of U. Now you consider the multiples of X. So whenever you take an element, if you consider its multiples, it is nothing but an ideal. So U is an ideal, multiples of X is an ideal. So if you sum up two ideals, it is also an ideal. Accepted? Yes or no? So you have the relation like U subset of U plus multiples of X subset of R. Obviously, it is true that this is a smaller set compared to this because it is sum of two values. It is only one thing. So this is a proper one. So U is a proper subset of this ideal. This is a subset of R because every ideal is a subset in the whole ring. So as per our assumption, U is maximal ideal. So what does it mean? Whenever you say that you have a maximal ideal, you cannot get an ideal between these two. This type of situation will not happen. If you say that U is maximal ideal, you cannot find an ideal which is between U and R, isn't it? So whenever you have a relation like this, we say that either these two are equal or these two are equal. The definition of maximal ideal. Can you recollect it now? Say. Therefore, by maximality of U, U plus X is equal to R. This is mandatory. Because these two cannot be equal. This is a bigger set, this is a smaller set. We know this. Hence the possibility is only these two must be equal. So what does it mean? Every element here will present in R. Every element in R will present here. Accepted? Since R contains the unity element, so 1 should belong to here. So since 1 belongs to R, you can say that 1 should belong to this set. So from this very property, you can say that from this very property, you can say that 1 is belonging to the set where each element is represented as sum of two values. So you can write 1 as some element say y plus alpha x, where y belongs to u. And for this relation, you add u on both sides. So applying coset properties, you have please check on the simplification what I did. Wherever you got a doubt, please ask. I will explain again. And tell me after noting the solution. Any questions for anybody? So you want me to explain that calculation part or not required? Is it understandable? Fine. Now see, x plus u is a coset. You are multiplying with another coset. You are getting the result as this, the identity. Just like the pattern that x plus u into something is giving identity. So what happens? This something is the inverse of this. So alpha plus u is the inverse of x plus u. As you know, whenever you have written the format like this, y belongs to the first set. This is multiples of x. So this is alpha x. So whenever you write a multiple, the element must belong to the ring. So you have alpha belongs to the ring. So alpha plus u belong to the quotient ring R by u. It is by default true. Because whenever you write multiples of x, it means that it is of the form set of x alpha such that alpha belongs to R. You are considering all the multiples of x there. So please understand the total approach what we did. In the first step, as we know that R by U is a field, it is enough to show that if you take any non-zero element in R by U, it possesses the inverse. It is the single condition we need to show as per the claim is considered. So I started with a non-zero element. So immediately I can say the element is not in the ideal. So I framed the sum of ideals thing. By the maximality of U, these two must be equal. So equal means both sets are having same elements. So one belongs to R, so that one should belong to the sum of ideals. So adding U on both sides and simplifying using coset properties, x plus u into something is giving 1 plus u for us. So you got inverse in R by U, hence it is a field. That was the whole approach. Clear to all? Please tell. Now I start with the main part. Shall I erase? Yes or no? It is a little bit lengthy solution, but you will enjoy the logic. You need to practice after the class session completed this result exclusively, because the solution is somewhat lengthy. It takes much time for you to understand. So coming for the main part, what is our assumption? R by U is a field. And what is our claim? U is maximal ideal. So it means that you are going to show that there is no ideal between U and R such that which is bigger than U and smaller than R. So we have to show like this. For this, let us take that u dash is any other ideal of R such that u is a proper subset of u dash, which is a subset of R. Let us take like this. It is our starting step, the supposition. As per the claim is considered. So our intention is, if you are able to prove that u dash is equal to R, it means that you have specified there is no ideal between the ring and u. So this is the thing you have taken actually. So I have taken that u dash is bigger than u. Now what happens? If these two become equal, then it means that there is no ideal between u and R. Accepted? If you have proved that u dash is equal to R, all of you agree? Please tell. So from the very point of this, u dash is subset of R, which is known to us. The other part you have to show R subset of u dash. So you are saying that the ring is subset of the ideal. That is actually you are proving here. So for this, it is enough if you just prove that the element 1 belongs to u dash. Because in the previous class, we have proved that a field has no proper ideals. At that, I have derived this context. The field will be equal to ideal if the unity element belongs to the set. Can you get the idea? We proved that part in the previous class. So whenever unity element belongs to the ideal, automatically ideal and ring both will become equal. So our intention is to show u dash equal to R. That means we have to verify R subset of u dash. That means it is enough to show that 1 belongs to u dash. This is the whole strategy we need to consider. So from this very step, as you taken that u is a smaller set when compared to u dash. So u dash contains more elements than u. So let us take that there exists x belongs to u dash such that x does not belongs to u. Because u dash is a bigger set than u. So immediately from this step, you can say that x plus u is not equal to u. Using the properties of cosets. So understand that x is an element in the ring. X plus u is an element in the quotient ring. So what you got here, x plus u is not equal to u means x plus u is a non-zero element in the quotient ring that you got here. As per our supposition, quotient ring is a field. So whenever you take the non-zero element, it possesses the inverse. So since R by U is a field, you can say x plus u into something is equal to the identity, where y plus u belongs to R by u. So multiplying the thing there, you have implies immediately you can say that, as I have mentioned that so x plus u is equal to 1 plus u if and only if 1 minus xy belongs to u. You can take either of the case. So you can ask if you have any questions here. So far what you got? Please tell me. Please let me know. So if you are clear, please take a note of it and then inform me. After noting, please tell. Right. Now, let us have a small picture here. You have taken 1 minus xy belongs to you. So, this is the thing you can consider. So, you got that 1 minus xy belongs to you. Since u is contained in u dash, so you can say that 1 minus xy belongs to u dash. We have xy belongs to u dash. Why? Because x is an element in u dash, y is an element in the ring. As per the product considered, because u dash is ideal, xy comma yx belongs to u dash. So you got two elements in u dash. So summing up these two, you can say that by closure law, one minus xy plus xy belongs to u dash implies 1 belongs to u dash. Therefore, R will become subset of u dash. Therefore, u dash is equal to R. Therefore, u is maximal. That was the conclusion of the result. So unless you remember the logic and pattern in which style you are going to prove it, you easily forget this one. So please take a note of the solution and we discuss with others. Please ask if you have any other queries with you. And after noting, please tell. Is the diagram gives the idea for you? What you did actually there? So whatever the question you have, you can ask with regard to this proof. If everyone is clear, I take the next concept. Fine. Now, after doing these results, we have some confusion with us. If R is a commutative ring with unity, then every maximal ideal is prime. This is very simple result. The solution or proof is followed by combining the two statements of the previous results in today's class what we discussed. Now see, in the question what he is saying, the ring what we have taken is a commutative ring and also having the unity element. Then if you calculate any maximal ideal, then it will become prime also. So in this gesture you can take that every maximal ideal is a prime ideal. That we can conclude. So how do we start? You take that UV is a maximal ideal of R. Just now we proved that R by U is a field. You accepted all? Yes or no? Just now we proved this. U maximal if and only if R by U is a field. That is the lengthy result what you proved just now. So immediately you can say that R by U is integral domain. Why? Because field implies integral domain. Every field is integral domain. Immediately you can say that UV is prime ideal. It is also a result, the first result of today's class. Now see, every maximal ideal is a prime ideal. I simply combine the two results, I got a new one. So in abstract algebra, by simply combining the statements of 2 or 3 results, you will get a new result. That is the beauty of abstract algebra. Okay? Please take a note of this. At this point, I want to discuss something interesting on the similar concept. After noting, please inform. Shall I proceed then? Okay. Now the question is, what happens if the word unity is removed? That means if R is a commutative ring, then every maximal ideal is prime. There is a question mark. So I have removed the word unity there. Then the answer is no. This question is also asked in the previous year papers. If you just take a commutative ring, every maximal ideal need not be prime. You can have a counter example for it. So that very example, I am going to write it now. So please take a note of this. So I take the ring as 0, 2, 4, 6. and hence the operation is modulo 8. Addition modulo 8, multiplication modulo 8. And I take the ideal, say u. The ideal u as simply I will take 0, 4. Now what happens, if you check for the properties of this ideal, it is a maximal ideal but not prime ideal. So we can easily verify. Now understand that you can apply the operation so we got 4 belongs to u, but 2 does not belongs to u and 6 does not belongs to u. Accepted? Under the operation, please tell. Accepted or not? So from this very perspective, it is not a prime ideal. What is the definition of prime ideal? If xy belongs to u, either x belongs to u or y belongs to u. This is the definition of prime ideal. The prime ideal definition. So here, this is satisfied. But this condition is not satisfied here. Please check. Therefore, it is not a prime ideal. Accept all? Now the question is it maximal? That we need to verify. It is also a very simple proof. If we apply the definition of maximal ideal, so let me say, if we consider the ring R, this is M you have taken, and say another ideal U here. So if I prove U is equal to R, then, sorry, see, this is U, this is, say, I. If I prove I is equal to R, then U becomes maximal. Accepted? The definition. So here you can say that basically ideal, if you take the operation plus, it is a subgroup. Accepted? So this is a subgroup of this and this is a subgroup of this as far as the diagram is considered. So whenever we have the group structure, we can apply Lagrange's theorem because these are the finite groups you have taken. So you can say that order of U divides order of I can say order of U divides order of I, and order of I divides order of the ring. So it means that 2 divides order of I and order of I divides 4. Isn't it? By Lagrange's theorem? Yes or no? So it is of the pattern that 2 divides x and x divides 4. What could be the possibility of x here? 2 divides x and x divides 4. What could be the possibility of x here? 4, isn't it? All of you agree or not? So the possibility for I is, you can say either x is equal to 2 or x is equal to 4. If you take x is equal to t, it is nothing but u is equal to I. If you take x is equal to 4, you say that I is equal to r. Therefore, u is the maximal ideal. It has no other possibility. So maximality is proved. It is not a prime ideal is proved. It is one good example. So if you take the ring with unity element, maximal ideal is always prime ideal. If unity is missed, then maximal ideal need not be prime. That is the conclusion we can take here. Fine. Please tell me. And please take a note of this. So at this point, I want to conclude our today's session, the discussion of ideals. So in the next classes also, I want to discuss some more concepts based on the ideals, which are the previous year questions also. And then we start with the new concept that Euclidean rings and homomorphism of rings. So many of the questions are also posed on that we discuss in the upcoming sessions. Okay. So thank you very much for your cooperation.